So good morning. That's great to hear. Lively this morning. My name is Hank Kenchington. I'm the Deputy Assistant Secretary for Research and Development in the Office of Electricity Delivery and Energy Reliability. We'd like to welcome all of you here today for this very special presentation of the Science Lecture Series. Today, the Office of Electricity Delivery is partnering with the Office of Science to sponsor this event, and I want to thank especially Dr. Pat Demmer, the Deputy Director for Science Programs, for helping make this event possible. Also want to thank our speaker today, Dr. Amit Goyal, and again congratulate him on his outstanding research and on receiving the Ernest Orlando Lawrence Award in Energy Science and Innovation yesterday during a ceremony at the Ronald Reagan Center. We are very excited about Dr. Goyal's talk today. Our R&D team at OE, especially Debbie Haught, our program manager for high-temperature superconductivity, are very familiar with Dr. Goyal's work, having sponsored his research efforts at Oak Ridge National Lab for more than a decade through our Advanced Cables and Conductors program. His pioneering research is groundbreaking and has far-reaching implications for how we as a nation can generate, deliver, and use electricity more efficiently. Today's lecture is special not only because of Dr. Goyal's world-class research, but also because it shows how research in the basic sciences can be coupled with research in the applied sciences to deliver important real-world innovations. Dr. Goyal stayed here overnight in D.C., tells us story we're thankful to Secretary Chu, for Secretary Chu, and I want to introduce Secretary Chu now, who will introduce Dr. Goyal. Dr. Chu was sworn into office as the 12th Secretary of Energy on January 21st, 2009. Prior to his appointment, he was the director of the Department of Energy's Lawrence Berkeley Lab, where he led the lab in pursuit of alternative and renewable energy technologies. He also served at the University of California, Stanford University, and AT&T Bell Laboratories. In addition to being the co-winner of the 1997 Nobel Prize in Physics, Secretary Chu is the holder of 10 patents and has published nearly 250 scientific and technical papers. Dr. Chu?
Thank you. So it's my job to introduce Dr. Goyal, but before I do, just two brief sentences about E.O. Lawrence. Certainly a legendary scientist, essentially the founder of what later became the first of the national laboratories, but this is way back in the 1930s, due to his invention of the cyclotron and the development of a team of scientists that helped make ever-improved machines. He also invented what is now known as team science to get larger and larger groups of scientists, very top scientists, engineers, people to actually do things in a unified way and really push back many of the frontiers of what later became high-energy physics, but also was an inspiration to the team of scientists he built up around him who later went out. Some of them stayed at Berkeley, but a lot of them went off and did many great things. So Dr. Goyal's following in the footsteps of many other E.O. Lawrence winners, of which at least 14 have gone on to get Nobel Prizes themselves. A little bit about Dr. Goyal. The story goes, and I could confirm that he was studying a fabulous school in Upper New York State called the University of Rochester. Happens to be where I graduated as an undergraduate in math and physics. A little bit before he was there. And the story goes that he was going to get a master's there and go to business school, and then learned of the Nobel Prize of Betnorz and Mueller, and the whole which was awarded very quickly, and that with Paul Chu and others, very rapidly rising critical temperatures, that was really exciting the community. There was, I think there were Woodstock. Were you there at that Woodstock conference? Okay. Yes, it was called the Woodstock of Physics, where this information just exploded and everybody got really excited about the possibilities, many of which are coming true today. And so because of that, he decided to stay in science, not go into business school, get a PhD in superconductivity and material science, superconductivity, and then from there he went to Oak Ridge National Laboratories. And so we're very grateful that science at least got one person instead of having the other, which was happening at that time and perhaps a decade later, of people going from physics to the finance world. So, you know, just from my humble point of view, actually does a lot more for the world if you keep some people in science, especially someone as talented as the E.O. Lawrence winner. So with that, I will just stop and just say how delighted I am that he's going to be giving this lecture. This is the first lecture in, I think it is, it's certainly, well, I don't know the previous history, but the idea I had was, you know, we have Fermi Award winners, we have Lawrence winners. Why not, when they're in town, find out who are good speakers and actually ask these people to speak to the larger community. So you're the first. You're going to be the Jackie Robinson of Lawrence, E.O. Lawrence winners giving talks. No pressure. But if they're good, we hope that this will mean that a larger and larger group of people within the Department of Energy are willing to take their time, bring their sandwiches here into this auditorium or sit at their computer terminals where it's streaming and listen to some of the work that our DOE scientists are doing for pushing back the frontiers of science and what they're doing to help in solving many of our problems. And so we hope that this is a great talk. I've been assured that you're a great speaker. Again, no pressure. But well, the floor is yours.
So I guess so first of all, I'd like to thank Secretary Chu for his comments and for his time. And certainly a great privilege and honor to be invited to give this talk. I'd like to thank the Office of Science for the Lawrence Award and for the wonderful ceremony yesterday. I'd also like to acknowledge everybody who was associated with the organization of the events related to the Lawrence recognition, including this talk. I'd like to thank the Office of Science for the support over the years, which under the High Temperature Superconductivity Program. And so what I'd like to do today is to take you on a journey, hopefully an interesting and an engaging one, from the point where these novel materials called high temperature superconductors were first discovered to where we are today, pointing in the right direction towards applications which made all the excitement when these materials were discovered. So the party began in 1986 when two IBM scientists, Bednorz and Mueller, discovered high-temperature superconductors. And when they did that, most newspapers and magazines in the world talked about how these materials would change the way we live in. As Secretary Chu pointed out, they were awarded a Nobel Prize a year later in 1987, and typically Nobel Prizes are awarded for work that's been done several years back, or many years back. So part of the reason why perhaps this occurred was the tremendous potential applications that these materials had. The superconducting transition temperature, or the temperature at which these materials go superconducting, had not changed much if you were to plot the transition temperature versus air until Bednorz and Mueller discovered these cuprate-based superconductors with a transition temperature of 40 Kelvin. That was very exciting. Not only that, Paul Chu and his group quickly discovered what's called the yttrium barium copper oxide superconductor, which had a transition temperature close to 90 Kelvin. And the transition temperature kept going up, the mercury-based superconductor being close to 140 Kelvin, and with pressures close to 160 Kelvin. Those were exciting days. We had reports of room temperature superconductors on a daily basis. They even occur now. So far, there's only been one valid report of a room temperature superconductor. And this was an ad in 1989 in the New York Times, which talked about the first superconductor that works at room temperature, referring to a symphony, but capturing the moment, the frenzy of room temperature superconductivity back in those early days. Now, despite the fact that the highest temperature superconductor was 140 Kelvin, the superconductor of choice for applications is the 90 Kelvin superconductor, yttrium barium copper oxide. And you may wonder why. And it has to do with the fact that the yttrium barium copper oxide superconductor has far better intrinsic superconducting properties. And that goes back to its crystal structure. So if you were to look at the crystal structure of two cuprate-based superconductors, one the YbCO, the other a bismuth-2223-based superconductor shown on the right-hand side, all this entire family of cuprate-based superconductors can be viewed as consisting of two-dimensional red planes, copper oxide planes, which are the superconducting components, separated by non-superconducting insulating or normal regions. And as you increase the distance between these red planes, the transition temperature goes up. But the material becomes more two-dimensional because these planes are not as close to each other. So mechanically, the material structurally behaves more mica-like, and the YbCO superconductor has additional structural component, which are these copper oxide chains. It makes it much like a traditional ceramic material, mechanically, as well as it is more three-dimensional. So intrinsically speaking, its superconducting properties actually are far superior to all the higher TC materials in the same family. Two key properties of superconductors: as you cool them down below a transition temperature called TC, the material goes superconducting, in other words, without resistance. And if you were to take, for example, the YbCO-based superconductor, a puck of it, cool it in liquid nitrogen well below the transition temperature, and you put a permanent magnet, a property of the superconductor is that it likes to behave like a diamagnet, expelling the magnetic flux lines, and hence the magnet levitates. Based on these two basic properties, one can envision a large set of applications of superconductors. So you can come up with an application tree. It is a branch of medicine, energy conservation physics, machinery processing, electric power and energy, transportation, electronics. Just in the area of electric power and energy, you can look at transformers, generators, transmission lines, motors, fault current limiters. Each one of these applications can be in billions of dollars. Besides the electronic-based applications, most applications of high-temperature superconductors require kilometer-long lengths of flexible wire capable of carrying large amounts of supercurrent. In the electric power industry, one can think about all these applications that I mentioned previously. These can amount to a large number when you look at the eventual application or the fully established application. So why do we need superconductors for all these applications? A very good answer is that resistance is futile. If you remove the resistance, you save energy. You can make these materials very compact and light. All these devices can be environmentally friendly. And then there are some niche applications which only superconductors can meet. So how do we make long lengths of wires of these superconducting materials so we can meet all these applications? As I mentioned to you, these materials are like ceramics. In other words, they're like the mud that you have in your flower bed, which, if you were to look under a microscope, would look something like this. You've got these grains, and you're trying to now combine this into a wire which is flexible and carries large amounts of current. And as you can imagine, that these areas which are non-superconducting and these interfaces that are present can't really be too good for current transmission. Well, ceramists all around the world came up with all these fancy techniques to make these beautiful microstructures. In fact, this was once regarded as a very nice microstructure, but when you made a wire of this microstructure and passed a current through it and measured the maximum amount of current that you could carry per unit cross-section as a function of the applied magnetic field, you found that the wire could only carry about 1,000 amps per centimeter squared, and that ability dropped tremendously when you applied a small field. And there were many reasons for this. And some of these are listed here. Chemistry at the boundary, microcracking. But the third one, the grain boundary misorientation angle. In other words, how much these grains on either side of an interface were misoriented with respect to one another had a big effect. What do I mean by that? So, an elegant experiment was done at IBM where they said, let's take a crystal and create an interface artificially by misorienting the two sides of an interface in a strontium titanate bicrystal, and then deposit a superconducting film so that the atomic configuration of that film adopted the same atomic configuration as on the surface on which these were being deposited, and then pass a current through the interface thus created within the superconductor. So you plot the amount of current that you're passing through this interface versus the amount of current you can carry within a grain on the y-axis as a function of the misorientation angle at this interface, independent of what the relative type of this interface was. And you found that in all cases above 5 degrees, there was an exponential drop in the amount of current that could be transmitted across the interface. So nevertheless, people were excited to make wires. So they said, well, how do I make a wire of a material which is a ceramic? So the only way you can think about it is really, you want to make it flexible, you attach it to a metal. But the only metal you could work with is something that would not react with it detrimentally, so people use silver. They got a silver tube, put a superconducting powder, drew it into a wire, made it into a coil, heat treated it in a furnace, did a rolling operation in the middle. Based on this, many startup companies were formed in the early 90s around the world. One of these companies was American Superconductor. It was formed by 3 MIT professors. Quickly, people formed or fabricated kilometer-long wires of these materials, of the bismuth 2223 wires, superconductor within silver. These wires were quickly used for application demonstration projects. In fact, here is a 3-phase cable that could be used for real applications located in Southwire, where all the power to the plant, which is a very big plant, the largest plant in the United States for making overhead transmission cable, all the power going in that plant going through these 3 superconducting cables in operation since 2000. But the question is, would this technology be economically feasible? So what were the application requirements? So if you were to plot the amount of current that you can carry per unit cross-section on the y-axis as a function of applied field, some of the best tapes made by American Superconductor, the performance is shown by the green curve. From 1,000, they went to 50,000. But was that enough? And the answer was no. What we wanted was a blue curve, which is really of a YBCO film deposited on a single crystal strontium titanate. You can see that it had a current capacity of over 1 million amps per unit cross-section, which sustained itself in high applied magnetic fields, which is important for all these most of these electric power applications. So the question is, how can we improve the performance of the wires? And the next question was, are these grain boundaries in this bismuth-based 2223 somewhat special that they don't get disrupted so fast, because you do have some capability of carrying current? So you're looking at a cross-section, silver all around, bismuth 2223 inside. We said, let's take a look at these samples. We removed the silver from one side, took an electron beam, and looked at the orientations on the surface of the superconductor, calculated the misorientation of interfaces, and color-coded the boundaries. And what we found was that one could trace percolative paths through green boundaries, which are low-angle boundaries, through much of the material. But in order to improve the performance of a kilometer-long wire, it would be impossible to dictate that process to align, for all the grain boundaries to align. So in the superconductor and silver model, it would be very difficult to get higher performance. So here are the real problems with the first generation wires. High cost of silver. 60% of the wire was silver. It had low performance because no way to control the interfaces. And as I mentioned previously, these are more two-dimensional than YBCO and had poor intrinsic properties to begin with. So the market needs for superconductor applications, we need at least 1 million amps per centimeter squared, 77 Kelvin, at the price of copper that you can buy in the hardware store. What did it mean technically for the wire? This meant that the wire had to be a long, flexible, single crystal but be made in a low-cost process so that it does meet the price-performance metric of copper that you can buy in the hardware store. Just to keep in mind, and just to give a perspective, the operating component of any computer is a silicon chip. The silicon chip is a single crystal. Even the silicon single crystal today can only be made in about 12 to 18-inch boules, about 2 feet long. And we wanted a kilometer-long wire, which is single crystal-like. Two ideas emerged to do this, or to meet this technical challenge. One is called rabbits, as an acronym, and the second is called IBAT. In both the processes, you have a superconductor layer, a contact layer, and a stabilizer layer at the top, but what's below the superconductor in these two layers, in these two processes, are different. In this process, called rabbits, we start with a metal foil, much like an aluminum foil, where all the grains within the material are aligned, and it's really a single crystal-like foil, and we deposit a few layers which have the same atomic orientation as the substrate. Then we deposit the superconductor, which also has the same atomic orientation as the metal substrate, and hence it's single crystal-like. In the second case, called ion beam assisted deposition, we start with a metal which is not textured, and the few layers are deposited, which are actually, again, are amorphous for planarization purposes. Then a single layer called the IBAT layer is deposited, which actually is single crystal-like. Another buffer layer goes on, and then the superconductor. This process was invented and developed entirely at Oak Ridge. This process was originally invented by Fujikura in Japan. It was worked on and perfected at Stanford, then at Los Alamos, with respect to the IBAT layer. And at Oak Ridge, we developed the lanthanum magnet layer, which goes on top of this substrate. So let me go into a little bit more detail. So as I mentioned, the first process, called rabbits, is just like an aluminum foil. We take a piece of metal, we roll it in a rolling mill, and we make a foil. But we roll it in a certain way so that it has a certain crystallographic texture. Upon rolling, we get essentially a soft aluminum sheet-like material. The only caveat is that all the grains in this material have their 100 plane parallel to the surface of the foil and a 100 direction aligned along the length of the foil. In other words, it's a mosaic, large mosaic, flexible single crystal, and because it's cubic symmetry, this peak is repeated 4 times. But in reality, just having one peak in this quadrant implies a single crystal, and the width of the peak shows you how good a single crystal it is. So then we deposit layers on top of this aluminum foil such that the layers adopt the same crystallographic orientation as the metal surface below, and that's what we call rabbits, rolling assisted biaxially textured substrates. The process starts in a rolling mill, in a class 1000 clean room, and the roll tapes are such that they're amenable for thin film heteroepitaxial growth. They can be made, much like aluminum foil, in wide widths. As I mentioned, when you look at the orientations, you have 4 peaks which repeat itself because of cubic symmetry, but the width here corresponds to saying that in a very large tape, all the grains are aligned within 5 degrees. Now, if you want to know what the grain structure is now, we can go back again to electron backscatter diffraction. Every pixel here is one diffraction pattern. So you can take 100,000 diffraction patterns and recreate the grain structure based purely on orientation. And when you do that, the green boundaries here are the low-angle boundaries, all less than 5 degrees. Now, if you remember a plot that I showed you at the beginning of my talk, if you're below 5 degrees, you can get lots of supercurrent transmission across the interface. So our goal now is to have the superconductor to have the same microstructure. Now, we have this aluminum foil. It's really a nickel-based foil, aluminum foil-like material. If you were to look at the atoms on that, you get these white atoms all arranged in a cubic lattice. But what we really want to do is we want to put a sulfur atom in every other unit cell to do a little atomic reconstruction of the surface. We do that only for one reason, because remember, we want to put the next layer down so that it has the same atomic configuration as the metal substrate below. And by putting a sulfur atom on every other unit cell, we get only one orientation, one heteroepitaxial orientation. If you don't do that, we get multiple orientations. So this is one step that we do after we make the foil. And this is better appreciated when you look at this atomic structure, Here's the nickel substrate structure with the sulfur atom on every other unit cell, looking down on the substrate or looking in cross-section. And let's say we want to deposit a simple cubic oxide like cerium oxide. When we have the C2x2 sulfur reconstruction, the first layer that we deposit is oxygen, then cerium, then oxygen, and then cerium. And the minute we deposit one unit cell, continuing on the other layers is much simple, or very simple. So we deposit the first layer in a reel-to-reel configuration. This is a cartoon. This is what the actual system looks like. We anneal it in a high temperature to form the nice texture. We leak a small amount of H2S gas, which automatically forms this surface reconstruction on the tape. We measure it by Auger just to make sure everything is going OK, and we deposit the first layer with a process called electron beam evaporation. We then put this tape into another system that we designed at Oak Ridge, now of course transferred to American Superconductor, the process, going from one reel to another with 3 linear sputtering guns, and we deposit 2 other layers called the diffusion barrier and the cap layer, and I'll get to that in just a second. So what we're doing in this process is we start with the metal tape, which is single crystal-like, and we can choose the composition of it to match the physical property of interest for the application. We deposit the first layer to get the right atomic orientation with this metal tape. We deposit this diffusion barrier layer to prevent atoms from here going up to your device layer. And then we deposit this third layer here to get a good match with the device layer, which in this case is the superconductor. And the basic stack is we have this metal substrate. We have 3 oxide buffer layers, yttrium oxide, YSD, and cerium oxide. Now, we can deposit these layers in 2 ways. We can either take this metal sheet, take it to a high temperature, and as we deposit the atoms actually line up in the right configuration. That's called in situ deposition. Or we can take this metal tape, dip it in a chemical solution, it could be water-based or oil-based, and then we can put it in the furnace, and during the heating process, the atoms line up. And that's called ex situ. And we can do either of these. So I showed you this plot in the very beginning, saying that the first generation wire technology was this green curve, and what we really wanted to be was the blue curve. And in fact, it turned out that one of the first few samples of the superconductor on this rabbit substrate was as good as the superconductor on a strontium titanate single crystal. And today, this same curve has moved up, straight up, where you're starting at 3 million amps per centimeter squared. American Superconductor routinely fabricates kilometer-long tapes now with a starting JC of 3 million amps per centimeter squared. The reason why these materials work well is because if you were to look at a grain boundary within the superconductor, you get a classic description of what is defined as a low-angle boundary with a pile of dislocations. As I mentioned, American Superconductor, currently the world's largest high-temperature superconductor company, has licensed this technology from Oak Ridge. After they deposit the buffer layers, they dip this into a chemical solution to deposit the superconductor. They heat treat in a furnace, and they form a nice single crystal-like superconductor. They deposit a contact layer, and then they mechanically slit. And what I mean by that is they make a white tape of the superconductor and then mechanically slit the tape into the right width for the application in question. And this is just glimpses of their factory that they have in Devens, Massachusetts. So this is their configuration. As I mentioned previously, we have 3 buffer layers. They have the same configuration. They have a superconductor. And they can make this wide. They can make the superconductor thicker. And as I mentioned to you, here's a plot of 0.5 kilometer of tape with a current carrying ability of 300 amps, which translates to 3 million amps per centimeter squared. So very good properties over length. These are the wires made using this process. These wires carry as much current as all these copper wires put together. That's because they have a very high current capacity. American Superconductor calls the wires amperium. Let me now go on to the second process, called the ion beam assisted deposition. So, as I mentioned to you previously, Los Alamos National Lab has been instrumental in taking the work from Fujikura and Stanford and taking it to a point where it could actually be commercialized. And they developed these areas in a roll-to-roll configuration. And this layer, the critical layer, ion beam assisted deposition layer, basically you have an ion beam coming in, which prevents atoms from any other configuration but one to deposit on a surface, and hence you get a single crystal-like layer. At Oak Ridge, we came up with this buffer layer called lanthanum manganate, which was necessary to come up with a high-rate process of making a long wire manufacturing process possible. And we worked with Superpower. We, in fact, transferred this LMO technology to them, where here's a 1 kilometer long tape, 1.2 kilometer long tape, showing you the degree of single crystal-like nature in this lanthanum manganate layer, which they now use in all wires produced by Superpower. So this is actually a very nice example, in my opinion, of taking basic science to commercialization. So we started with work which talked about grain boundaries in bismuth 2223. I didn't go into this thallium 1223 material, again related to texture, but we identified the need and we identified what we ideally need. We then used applied R&D to create single crystals by the mile, and then we transferred this technology to manufacturing and commercialization. Today, all wire made worldwide is made using one of these two techniques, high-temperature superconducting wire in all the countries. So this was the first holy grail in meeting applications for superconductivity. And when this was realized, we thought the work was done. But more often than not, as you all know, it never is. So quickly, a second holy grail was identified. That is, we had to enhance the vortex spinning within these wires. What do I mean by that? So all superconductors look like Swiss cheese. What I mean by that is, in Swiss cheese, you've got these holes that go through it. In a good superconductor, you've got these flux lines in yellow which go through it. And if I were to take one of these flux lines and take them out to the right, and the field is going in this direction, if I now want to pass a current through this wire, indicated by this arrow here, there's a Lorentz force which moves this yellow flux line in the perpendicular direction. And when this flux line moves, it causes resistance, destroys superconductivity. So in order to get good properties, the name of the game is that you need to immobilize these lines so that they cannot move. Well, the catch is these lines are only nanometer in size, and they're separated only by nanoscale dimensions. The question is, how do you do that? It seemed like a seemingly impossible task until there was an experiment done, again an elegant experiment done by IBM. They took a single crystal of this material, of the superconductor, and bombarded it with heavy ions. These heavy ions are energetic ions. They go through the single crystal, and as they go through the crystal, they amorphize wherever they go. They create these damaged tracks. So these tracks become non-superconducting. When you apply the magnetic field parallel to these tracks, you immobilize the lattice, and you get a big peak in the amount of current you can pass through the superconductor. Well, this is all nice and good. The question is, how do we translate this to kilometer-long wires? If you use heavy ions, you'd make the metal substrates in those wires that I talked to you about radioactive, and besides, they'd be far more expensive than pure copper that you can buy in the hardware store. So this quickly became the second holy grail in the field. In fact, we had just finished working on the second generation technologies to make these single crystal wires. The view in the community was that these wires are already so good, it's probably going to be impossible to make something even better. But then there were some very important advances made, or pieces of work that were done, first by the Air Force Research Labs, and second by Los Alamos and the University of Cambridge. They showed that we can, indeed, put nanostructures within single crystal superconducting films on single crystal strontium titanate substrates. In both cases, in this case is being something called 211 within a superconductor, and in this case being a whole random set of barium zirconate particles of this distribution within the superconductor, and showed that you could improve the performance of a single crystal film. The question was, can you realize some more ideal microstructures like the Swiss cheese microstructures that I just showed you about? So at Oak Ridge, we came up with this method called self-assembly, where we use a self-assembly process. And of course, I wanted to mention that all of this increase in performance has to be done without adding cost. So here is an example looking at cross-section into a YBCO film, where we've created these nanodots of aligned barium zirconate non-superconducting columns. And if you were to look down this way in a TEM, they would look like this. These hole-like features are barium zirconate columns. And you can see that this structure now is starting to resemble the Swiss cheese microstructure. And if you take it slightly higher in magnification, you can see that these are indeed nanoscale in dimensions and separated by nanoscale distances. You can go still higher in magnification into one of these dots and look at the atomic configuration, and you can see that they're separated by, they have these 4 misfit dislocations, which in a column all align up. And so theoretically, this should be a very good way of pinning this vortex lattice that I mentioned to you about. And so indeed, when you put these columns inside a YBCO film on a rabbit substrate that I mentioned to you about, all the open circles here are for, in all these temperature measurement temperature regimes of 3 different temperatures, are without these columns and with these columns. And you can see that there's a massive enhancement at all magnetic fields and temperature of measurement temperatures. And if you look at the angular dependence, that's the amount of current that you can pass as a function of applied field, you can see that without these and with these, there's a massive enhancement. Well, the next question was, can you actually sustain these over thick films? Because you really need thick films which can carry large amounts of current for applications. And the answer is yes. We can actually start these nanostructures on the top of a layer on a rabbit substrate and go all the way up to 3 microns. That's the work reported in this 2006 paper, where these columns that you're seeing, nanocolumns, go all the way to the top. When you have these columns and thick films, you start to meet application requirements, which are in the amount of current you can pass per unit width for a variety of applications, including rotating machinery, military applications, and cables. But of course, the next question is, can we improve this even further? And for that, we ask some of the basic fundamental questions. Well, how are we really doing this self-assembly? How do these columns form? Can we change their orientation? Can we make more complicated structures? Can we make this even better? And the answer is yes. In fact, we did a lot of this work so let me actually go back a little. We know that this occurs by strain minimization. But to show that it occurs by strain minimization and that these nanodots are aligning up within the material by a self-assembly process to minimize the strain energy, we can do that. We can do an experiment by separating the strain here by changing the distance between 2 nanodots. And we can do that by actually doing a different kind of a deposition than the way we were depositing or making these materials by depositing the red and the green atoms, one being the superconductor, one not being the superconductor, together. So when we do that, we can actually model this too, using theory and modeling. We can come up, this is the only equation that I have in my talk. We came up with what's called the modified Kahn-Hilliard equation. And we could theoretically say that if we had a thin spacer layer between nanodots, we would get alignment. And when we have a thick spacer layer, we won't get alignment. So we said, well, let's see if we can experimentally prove this. So in the next view graph, we start out with the microstructure that I showed you previously with these nanocolumns and these 3-micron films. This is a plot of the amount of current you can carry when the field is applied parallel to these columns versus in the perpendicular direction. You can see in the perpendicular direction you have less ability to pass current than you have in this direction. So we actually really wanted to get from here to here so that we have the same amount of capability in both directions. Well, we can do that. By modifying the strain, we can align these nanocolumns in a perpendicular direction to the c-axis. And we can go to here where we've got these columns aligned in both directions. And then we get this massive enhancement that we were looking for. Now, if you were to then look at the angular dependence of these 3 microstructures that I showed you, going from here to here, you can see that this red curve here was the curve. This is the amount of current you can pass as a function of magnetic field orientation to the c-axis. And you can see this red curve is without these nanostructures, and the blue curve is with these nanostructures. And you can see that you can get this massive enhancement. Well, everything I showed you was a laboratory scale result using pulse laser deposition. We, of course, need to make kilometer-long wires. So here's an example of the same structures done by a process called MOCVD that Superpower is using to make kilometer-long wires at no added cost. They are now fabricating kilometer-long wires with these nanoscale columns with world record performance on a regular basis. This is an example of a plot of close to 0.6 kilometers of material having some of the best performance in field. And this is indeed also one of the first examples of scaled-up use of nanotechnology in general, not just in superconductivity, where for an advanced application, you're using nanotechnology, in this case self-assembly, in kilometer-long lengths. So again, this is a fine example of basic and applied R&D moving to manufacturing and commercialization. In fact, here the basic and applied worked hand in hand, so it's difficult to kind of separate the two out easily. So we had the first Holy Grail, then we had the second Holy Grail, and we thought the work was done now. But of course, as I mentioned, there's always more to do. So we quickly learned that there are some applications where AC losses are really quite important. And here's the problem with AC losses. So we made this really nice wire, a single crystal-like wire, has got nice nanostructures, carries lots of current and field. What's the problem? Well, the problem is that in applications where AC losses are important, there's a hysteretic loss that comes from the superconductor layer. In order to reduce that loss, you have to take a laser beam and cut regions through it to create filaments to reduce the AC loss. And you needed filamentization. Then you had to twist and transpose these filaments so they cross out the field so the AC losses go down. Well, as you can well imagine, this will add cost, and it'll be difficult to do in a tape geometry. So what the field really wanted was what one would call is a round conductor, a round wire, but with the same constraints. We still needed a single crystal wire. And we wanted to avoid the metal because the metal can cause some eddy current losses. So how do we do that? Well, we came up with a process that we call SIFs, structural single crystal faceted fibers. These are sapphire fibers with two planes running parallel to the fiber, which have a certain crystallographic configuration, and I'll tell you why we have chosen that. And then we deposit superconductors on them. So why faceted, why structural, why Al2O3, sapphire? Well, optical fibers are used in many applications. They are round. Even if you use crystalline optical fibers, they are round. If you deposit an isotropic material like superconductor, you'll have the orientations varying all around this round wire. So we have to have well-defined crystallographic planes for the material to grow in, and hence faceted. Why structural? Well, it turns out we need to be able to make this at very high speed. Otherwise, it won't be cost competitive with the technologies like the second generation technology. And structural means it has some defects, not as low defect density as optical fibers. And sapphire, because you see, there was this whole industry called the metal matrix composites industry, with a lot of work done on sapphire fibers. So that's the only material that's actually, there's a lot of technology development, but the big problem with that is the sapphire fibers are hexagonal or rhombohedral. In other words, if you were to deposit a cubic material on a hexagonal material, you get multiple orientations. So it's not going to serve your purpose. So we played a trick. If you were to look at the unit cell of sapphire, there is one plane there which is pseudo-cubic. So we said, let's make these planar facets out of this pseudo-cubic plane, and that's called the R plane. So we make these materials, we grow buffer layers in superconductors, and well enough, they carry very good currents. And these fibers are really strong. These are measurements made at NIST, 310 gigapascals, and the UTS being 1508 MPa. We can make these in multiple fibers, and the goal really is to adopt a process that was done by NASA for making structural metal matrix composites. Now, this work has not been scaled up yet, but that could be scaled up following a similar path. And these fibers really look like fishing wire, the fishing line wire. They look identical to that. Anyway, so the point is that these fibers can be made, they're strong, and we can grow superconductors on them. So let me now talk about HTS markets and applications. So wherever large amounts of power are involved, where electricity is used, superconductors can have an impact. When you go from power cables to fault current limiters, to motors and generators, transformers, superconducting magnetic energy storage, there are all kinds of defense applications like Navy motors, Navy ship shielding, degaussing, magnetic separation, maglev trains. These are disruptive technologies. They can have higher performance, smaller size, and at times lower cost. Here is the portfolio from one of the companies that we've worked with over the years, Superpower, talking about the items in green, which are near-term applications between 1 to 5 years from now, mid-term applications in 3 to 7, and longer terms in black, 5 to 10 years. And you can see that there's a whole range of applications in the energy, defense, transportation, industrial, medical, and science and research, translating from fault current limiters to cables to transformers. I'll talk a little bit more about these wind turbines and going to space exploration as well. So here's an example of superpower's cable application. This was energized in the grid in January of 2008. So this is an actual superconducting 2G-based cable that is supplying power to 25,000 ohms in Albany. And this is 3 superconducting cables within a cryostat. Here's some of the work that American Superconductor has been engaged in. They've got a cable with LS cable in Korea, something which was installed 500 meters, a cable in the grid in 2011. The Long Island Power Authority, they've got a 1G cable operating since 2008, and they're going to be putting a 2G cable in this year. And the New York cable, which is scheduled or planned for 2014. And here's the biggest order that has been received by American Superconductor to date of 3 million meters from South Korea, LS cable again. They plan to make a 10-kilometer HTS cable installation. There are a number of applications for rotating machinery and magnets. Here's an example for a 3.6 Tesla magnet for particle beam therapy or proton beam therapy for cancer, linear induction motors, racetrack coils for generators that can be used for wind turbines, solenoid coils for the muon collider, magnets, NMR for drug development and protein discovery. Some of the largest, highest field magnets have these 2G inserts. In this case, this is a 35.4 Tesla magnet out of the National High Field Magnet Lab in Florida. Smart grid. We know that we've got these substations. When you can easily have a lightning strike, for example, and one of the substations goes out. So you want to have some redundancy where you have substations connected. When substations get connected, you get a risk for fault currents. When you get fault currents, you can damage expensive equipment in the grid. And so the ideal scenario would be that you have some sort of a fault current limiting capability, and superconductors offer that. Because superconductors, when you pass more than a certain amount of current, they go resistive. And so here's an example from American Superconductor of a fault current limiter wherein with the HTS, you don't get too much fluctuations. Without it, you can get a large amount of fluctuations in the current. And so this can actually be incorporated within a device, or it can be a standalone fault current limiter. For the wind turbine application, there is well known that offshore winds are strong and steady, but that the cost of conventional solutions are not there to a point where these applications can take off. So if one were to increase the amount of power that an individual turbine generates, it will improve the economics dramatically. But it turns out that this nacelle and hub are really very, very heavy. So you really can't scale these much further. So you have to do something to increase the power that is generated from a single turbine. HTS generators offer to do that because you can double the amount of power that you can generate out of the same turbine. Of course, this hasn't been demonstrated yet, but all indications are that it would. And this is shown again here in a view graph from American Superconductor, wherein if you were to take a conventional drive wind turbine, the weight is typically about 500 tons, and you can generate a power in the regime of 5 to 6 megawatts. If you go to a superconducting generator on this turbine, you could generate 10 megawatts at the same weight. And so the power density of HTS generators is the point in question here. Again, they would use the same 2G wire that I talked to you about. We're talking about renewables. We know that we have got wind generation taking place here, solar as shown here, and geothermal as shown here. But where it's being used is indicated by the green arrows. And a potential application, again, this is a more futuristic application, the long distance transmission through DC superconducting cables. And this is a standard right-of-way that's present for overhead cables, and a DC underground cable would take that much space. Again, it's a possible way of rapidly transmitting large amounts of power from where it's generated to where it's being used. So, much like the solar industry, when you talk about the wire, much like the solar industry, the HTS wire price performance metric needs improvement. If you were to just scale with economies of scale, you have these linear extrapolations which take some time to occur. R&D innovations will help achieve these points, price performance metrics, for large-scale commercial deployment earlier. Let me just say a few words about the global competition before stopping. So I'd just like to thank some of the people from Korea, Europe, and Japan who have provided some of the input for these set of slides. So if you were to look at Europe and Asia in terms of 2G HTS wire fabrication, first I'd like to mention that all of these fabrication that's been occurring in all these companies, they're either working on rabbits-based wire or the IBAT-based wire that I just mentioned to you about. Second, you can see there's some large companies, Bruker, Nexans, and in Japan especially, Fujikura, Sumitomo, Furukawa, Showa. These are all very large companies. InnoPower in China. There's a new company in Russia also established. This is for the wire. I just want to give you a glimpse of all the work that's going on around the world very quickly. So we talk about the power cable or transmission. You can see again that there are large companies involved, NKT Cables, Nexans, again, Sumitomo, a very large company, Furukawa Electric, Fujikura, Showa. Talk about fault current limiters that I mentioned to you about. You can see the space is very crowded, both in Asia and in Europe. And it's only increasing. Look at HTS transformers, very large company, ABB, multi-billion-dollar company, Siemens. Again, if you look at Japan, lots of large companies involved. Superconducting magnetic energy storage. I didn't get a chance to talk about it, but this PES offers the possibility of quickly charging and discharging large amounts of current in multiple times, with a lifespan far greater than conventional chemical energy storage. And again, there are very large, great number of companies working in Asia and in Europe on this application. And rotating machinery. I'd like to point out that Kawasaki, Sumitomo, and Siemens, again, which is a very large company in the rotating machinery space, are all very excited by these applications involving motors and generators. So let me just finish up with the last two slides. One is just a comparison of the timescale that it took for optical fiber to get commercialized. It was fully developed really by fiber optic by Corning in 1967, and they had first usable lens in 4 years later. And it was not until 10 years later when MCI placed the order of 100,000 kilometers, and then 28 years later, clearly by 1995, it was everywhere. In the case of HTS, the first generation wires were made in 1989. The first second generation wire came out in 1996. 16 to 28 years time frame where we are right now, we start to expect to see applications taking place. And with that, let me conclude by saying that DOE funding truly resulted in the second generation and the third generation HTS wire technologies, which are being used worldwide. And it was, again, the DOE program which resulted in the creation of ordered nanostructures within these wires, which is essential for meeting the performance requirements. Prototype application demonstration projects are ongoing, and we certainly hope that the large-scale applications of high-temperature superconductors will be realized in the next 5 to 6 years. And that continued R&D is certainly needed to get the price performance metric of these wires to a place where applications can occur, and for the US to enjoy continued leadership globally. I'd like to acknowledge the US DOE HTS program for allowing work of scientific discovery and technological innovation at the interface of basic and applied work to actually happen. Of course, all in line with the mission relevance for the program. I'd like to acknowledge Debbie Hott, Jim Daly, and Pat Hoffman, and others in the OE office. I'd like to acknowledge the contributions of the Oak Ridge team over the years working in this area, and really also the broader US DOE HTS program, particularly the work that went on in Los Alamos, which was very extensive, at Argonne National Lab, Brookhaven National Lab, NIST, Florida State, and other universities like Stanford and MIT. And American Superconductor and Superpower, two companies that we've worked with very closely over the years. Thank you very much.
So I think we have some time. We're actually over time, but I think we can take a few questions. Front Kip, can you speak up, please?
Yeah, thank you very much for your presentation. It was very interesting. Can you speak a little bit about the issues there are with cooling the material and keeping it cold?
Yes. So cooling issues for discrete applications like motors and generators, depending on the application temperature, in all likelihood one could use cryocoolers for that. And even if one is using cryogens, it is a self-contained application. So the real issue, or the debate I think comes in with cooling, is when you have long-distance transmission. So even in short-distance transmission, what is envisioned is a cryostat which has liquid nitrogen in it, and it is pumped at certain intervals to keep the temperature even below liquid nitrogen. Now, when you look at underground transmission cables, they have a different fluid filled in them anyway. So in a sense, on one hand, it may seem that while it is true that cryogenics will add cost, in some applications it actually may provide some degree of stability as well. For example, in superconducting magnetic energy storage, it has been argued that because we're not involving any chemical change, the usual mechanisms for degradation of batteries are not applicable in this case for superconducting magnetic energy storage. In fact, you can go infinite number of times back and forth. So I think cooling is certainly an issue to be considered in the overall design of a device, but it's certainly, there's nothing which shows that it is a showstopper or a fundamental limitation. And it's partly because the liquid nitrogen that one could use, and that was really, in fact, what created all the excitement in the very beginning, because liquid nitrogen is the same price as mineral water. So I think certainly for discrete applications, the benefits far outweigh the complexity offered by the cryogenics.
Hi, I was curious on the first of the second generation, you mentioned that you still use silver in it, and then the other one that I can't remember which ones
Right.
are, I'm sorry, they didn't look like you used silver, it looked like you used copper, and I was curious if the first one was way more expensive than the second because of that.
Right. So the first generation technology has a superconductor in contact with a metal, and there it's all silver. In the two second generation technologies and the third generation technologies, there's a very thin silver layer, very thin. So it's a very small fraction of the cost, so it's a non-issue. So then you have silver, then you have copper. That's really a stabilizer layer for just in case of local loss of superconductivity because of a defect. So there's a parallel path provided, so the current can quickly go there and then bypass the defect and then come back into the wire. So it's a stabilizer layer.
So structurally, with biaxial pneumatics such as yttrium, barium, copper, oxide, how is it more conducive to superconductor applications? It has three facets, or is it that what makes it more conducive to superconductors, to becoming a superconductor? To being used in superconductors, or
perhaps you're asking the question, why does it become a superconductor?
Why is it easier for it to become a superconductor than
any other material, for
yeah.
example? Well, that's a very good question, and I don't have a very good answer for you. Okay. So one of the interesting things about superconductors is that certainly the cuprate superconductors and the newer superconductors, we don't have the exact science figured out as to why these materials superconduct. There are a lot of speculations, and they're rather complicated, but typically the view for the older superconductors was that you formed a pair of electrons which, when traversing a defect that normally causes resistance, they have opposite spins and they cancel out. Now, the pairing mechanism that goes on, which makes two electrons coupled in, for example, high-temperature superconductors is different. And what it is exactly, there's no complete consensus on that still. So if you were to ask the question, a simple question, if I wanted to come up with a new superconductor, what material would I work on, and which material will do it? Can I predict it? Those answers are very difficult. I don't think they're really there.
So, but if you could give its structure?
Oh, you mean the yttrium copper? Yes.
Yeah, its structure has three
Of
facets
course.
and then two mirror.
Of course, it is completely related to those structures, but when you dig down deeper into it, to the really fundamental reason as to why that material superconducts and what actually causes it to become a superconductor at 90 Kelvin, the right answer is that in the scientific world, the consensus is still not there.
One more?
Amit, you gave an interesting geographical view of the distribution of industry involved, but these are really electric equipment manufacturers, and the customers are really the electric utilities.
Right.
Can you comment on their involvement in adopting this technology?
Yes, and it's an excellent question. So it is correct that the final customer is a traditional customer, the utilities. So in order to accelerate these applications, one would argue that the utilities have to pave the way for it. So the next question would be, what would make the utilities pave the way forward to it for these applications or for modernization of their equipment, and hence they can maybe adopt some of these technologies. And I think that driver, perhaps, there has to be an increased driver for the utilities to move in that direction. And perhaps that would take some influence from, let's say, the governmental bodies, I would suspect, because the utilities definitely think on a shorter-term basis than a longer-term basis. And many of these applications in superconductors, as you can appreciate, things like transformers, where the economics is there when you look at the longer-term picture, but from a shorter-term picture, one would argue that compared to conventional options, it's not looking as rosy. So I think you're right that from a final customer base, from the utility base in the electric power industry, there has to be some sort of an impetus, and that is why when you look at some of the developing countries, especially China, where they're adopting new infrastructure, it is envisioned that they may adopt some of these technologies before some of the more developed areas.
Okay. Well, thank you all very much. We have to let Dr. Goyal go so he can go get his Nobel Prize. So if you give me a hand, please. Thank you.